Hey, Mr. Harridan here. Welcome to my dining room table in my La Casa de Harridan. We're going to go over some calorimetry today. Here we go. Calorimetry is a technique used to measure heat transfer. As this will be the first time I am trying to make a video for you on my phone completely. We'll see if this works. Okay. So we're trying to measure heat transfer in a reaction process. Usually we have an insulated container measured at either constant pressure or constant volume. Okay, so here's how this works. First of all, we're going to make a huge assumption here. We're going to assume that no heat is gained or lost to the surroundings. The surroundings in this case would be the actual calorimeter here. Okay, the air, anything that is not the substance in the water. So here's our goal here. So calorimetry, you're usually burning substances. So you're going to have a substance here. And since we are burning the substance here, this is going to be delta H is negative. So this is going to be exothermic. So the heat is lost by the substance. Learn how to spell lost, Mr. Harridan. L-O-S-T. Okay. And usually you're going to have some water in here as well. The water is going to try to gain all the energy that is lost from the substance. So this is going to be endothermic, positive delta H. So the heat is gained. Okay, so the assumption here is that all the heat is transferred to the water that is lost. Okay, we're not going to have any heat going to the insulated container, the air, the thermometer, whatever else we have in there. Okay, so calorimetry is based off of this equation here, the one that we saw in our phase change diagrams. Delta H equals m Cp delta T. Remember, delta H can also be small q here. Technically, I'm supposed to use Q for all these, but I'm a delta H guy. Okay, so here we go. Let's look at our problems here. Example 11.4, which I have no idea if that's the number that's actually on your paper. 0.303 grams of sample of sucrose, which is sugar, is burned in a calorimeter at 240 grams of water. During the process, the temperature of the water changed from 22.53 to 27.55. What is the heat change of the sugar? Okay, so first we have to figure out, let's look at what we have here. We have some sugar. Okay, the sugar is our substance, so this is going to be delta H is negative. It's going to be exothermic, and we have 0.303 grams. Okay. Then we have some water here. And I'm having issues with my setup right now. Water. Don't move your hand there, Mr. Harrison. Okay. Delta H is positive. It's going to be endothermic. We have a mass of water of 240 grams. We have a Cp of water of 4.184 joules grams degrees Celsius. And we have a temperature change. You have to do final minus initial here of 27.55 minus 22.53 degrees Celsius. Okay. Oh, Mr. Harridan, why are you can be folding the paper in half here to make this easier on you, so your hand isn't in there. You know this, Mr. Harridan. Come on. There you go. Fold the paper in half so you can get it up to the top of the screen so the students can see what you're doing. There you go. And that way your hand is not in the way. Okay. Smart, Mr. Harrison, smart. Okay. Okay. So in these calculations, I know it says, what's the heat change of the sugar? You gotta start with water. Just like in those reaction stoichiometry problems when it asks for how much product you produced, and you have to start off with the mass of the reactants. Yeah. Yeah. So here we go. So we're going to do what I call a water calculation here. Water. Oh, so glad you moved the paper, Mr. Harridan. Now you can actually reach it and write on it. Okay. We're going to do what we do as a delta H equals mCp delta T. Okay. Now you have to use the mass of the water. You don't use the mass of the sugar here. You use the mass of the water. So it's 240 grams because you have the Cp of water is 4.184 joules grams degrees Celsius. And you have a delta T here, when you subtract those two numbers, of 5.02 degrees Celsius. That is your delta H. So delta H is going to be positive 5040 joules. Okay. This was gained by the water. But remember, our original question is not about the water. It's about the heat change of the sugar. Well, remember our assumption here that we're assuming that all the heat that was lost by our substance is gained by the water here. So the delta H of the sugar is negative 5040 joules, which is the heat lost by the sugar. Okay? Because we're assuming all heat is transferred to the water. Okay. So that's why those values are the same, except one is positive because one is gaining the heat. That's endo. One is losing heat. That's exo. Okay, next part here. Okay, hopefully we can see what I'm doing here. Okay. Okay. Very frequently, the problem asks us to find the kJs per mole. This is basically a value showing us how much kilojoules are released by 1 mole of substance. Good fun there. Okay, so let's find the kJs per mole of sucrose. So here's the steps for doing this here. Step 1, find kJs. Step 2, find moles. Step 3, divide. Okay. So first thing here, let's remind you about how to go from joules to kilojoules here. Remember that there is 1 times 10 to the negative third kilojoules in 1 joule. So we know our sugar burned 5,040 joules. Joules on the top, joules on the bottom. What are we going to convert to? Kilojoules. 1 times 10 to the negative third kilojoules. And we get an answer of negative 5.040 joules. Nope. I keep doing that in these videos. I've had to redo this video like 5 times. Kilojoules. Okay. Now, let me show you how we go from grams to moles. Hopefully you remember. Dividing by the molar mass on the periodic table. Okay, so for starting off with 0.303 grams of sucrose, which is C12H22O11. Okay, grams on the top, grams on the bottom. What are you going to convert to? Moles. Swish, swish. What does the tape say? 1 mole. Grams. Molar mass, trust me on this one, it's 342.34. you divide those two numbers, and you end up getting 8.85 times 10 to the negative fourth moles. So then you take those two numbers and you divide them here. So you got 5.040 kilojoules divided by 8.85 times 10 to the negative fourth moles. And you get an answer of negative 5.70 times 10 to the third kilojoules per mole. Okay, now if you actually look that number up, issues. If you actually look that number up in a table, that was interesting. It's actually listed as a positive number, okay? Because here's what you have to understand, okay? Since this is a heat of combustion, all combustions release heat, okay? Which means delta H is negative, which means it's exothermic, which means heat is on the product's side. When they actually list these in the table, they actually list them as positive because we all know they're exothermic, all the heat of combustion. Okay. Okay, let's see if we can do these other two problems really quick here. Okay, we're going to figure out what is the heat change of 1 gram of sample of octane here. So we're going to start off with some octane. This is delta H is negative because it's exothermic, and we have 1 gram. Okay. Then we're going to look at our water here. See how much water is in our problem here. We have 1,200 grams of water. As I can hear my dog getting water right now. 4.184 joules grams degrees Celsius. And we have a temperature change final minus initial of 33.20 minus 25 degrees Celsius. Okay, so now we got to do a water calculation here. Water. Because it would be too easy to start with the octane. So we have to do delta H equals MCP delta T. So we're going to have 1,200 grams. 4.184 joules grams degrees Celsius. And delta T here I have as 8.2 when you subtract those numbers. Okay, so we have a delta H here of positive 41170 joules gained by the water. I don't really worry about sig figs and these thermodynamic problems, but probably we should write all these answers as significant figure scientific notation if we were doing that. So since this is the gain by the water, we know that there was negative 41170 joules lost by the octane. And just so you know, these positive and negative signs are just telling me if the heat's lost or gained. Okay, that's all it's really telling me. Okay, so here we go. We're going to calculate the heat of combustion here in kJs per mole. So you know what I'm going to do, right? I'm going to find kJs. I'm going to find moles, and then I'm going to divide. So I'm going to take my negative 4117 joules. 1 joule goes on the bottom, 1 times 10 to the negative third kilojoules goes on the top. And we end up with negative 41.170 kilojoules. Then we got to do our grams to moles here. So we're going to do 1 gram of octane, molar mass of octane. It's 114.26 over 1 mole, which equals 0.008751 moles when you do it. Now you're just going to take those two numbers and divide them. And you end up with your kilojoules per mole here, which is negative 4704 kJs per mole. Yeah, I've been using the raw molar mass for octane on this problem since 2016. That's what I figured out yesterday. So then I had to go back and redo it. Awesome. Okay. Now, example 11.6, last one we gotta do here. Let's see if I can do this in 5 minutes. Okay. Here we go. 15 gram sample of copper is heated to 100 degrees Celsius in boiling water bath. The copper has been moved from the calorimeter, contains 100 grams of water. CP of water is 4.184 joules grams degrees Celsius. Initial temperature is 25. Final temperature is 25.35 degrees Celsius. Assume no heat is lost to the environment or to the calorimeter. Okay. Here's how we're going to do this one. Pretty much the same setup that we've been doing here. So we're going to have the copper. Copper's exothermic. Delta H is negative, correct? Okay, we have 15 grams of copper. Now, there's actually a temperature change of the copper because the copper started at 100 degrees and it went to 25.35 degrees because that's the equilibrium temperature when it all bounces out. So to do the temperature change of the copper, it's 25.35 minus 100. Okay, that will come into play later. Okay, because this problem's a little different than the other ones. Okay, now we got to do our water. Okay, water, we have 100 grams. We have 4.184 joules grams degrees Celsius. And our temperature change here is going to be 25.35 minus 25.00 because the initial temperature was 25 for the water and the final temperature is 25.35. So you can see that the water is getting warmer and the copper is actually getting colder, right? Because it's losing heat. Yes. Okay, so now we're going to do our water calculation again. Water calculation. We're going to do delta H equals mCp delta T. Delta H equals 100 grams times 4.184 joules grams degrees Celsius times the change in temperature, which is 0.35 degrees Celsius. So delta H here is equal to a positive 146.44 joules. This was lost by the water. Okay? Because the answer to the question is calculate the heat change of the water. Okay, I did that. Okay, part B. Determine the heat change of the metal. Well, since the water gained 146.44 joules, I know that delta H equals negative 146.44 joules. Why did I write loss there? Good thing I caught that, Mr. Hero. This is actually gain, correct? Let's see if I did that on the other one. Nope. Because the water is gaining energy because it's positive, Mr. Hero. The copper is lost by copper. Okay? Because again, we're assuming that all the heat is transferred over here. Okay, now, let's look at this last question here, which is a little different. Using the heat change of the metal, calculate the specific heat of the metal. So now we're going to do what I'm going to call a copper calculation here. You're like, what? Which means I'm still going to do delta H equals mCp delta T. I know the delta H here is negative 146.44. I know the mass of the copper is 15 from over here. Cp is right there. And then delta T here is 25.35 minus 100, which is a negative 74.65 degrees Celsius. And when I do all this math here, eventually, because this negative and negative is going to cancel and get me a positive Cp, the Cp is equal to 0.1304 joules, grams, degrees Celsius. This was in joules, this was in grams, and this is in degrees Celsius. They didn't cancel, so that's why I'm left with those units. Okay, you guys are champions. The legend is out.